Or I'm focused on the work that I got. This is problem 1774, closest dessert cost. So let's get right into the problem. Okay, so you would like to make dessert and are preparing to buy the ingredients. Okay, you have N ice cream base flavors. All right, so N ice cream base flavors. So maybe some vanilla, chocolate, mint chocolate chip, Rocky Road, all the classics, all the hits, and M type of toppings. Okay, so M toppings, maybe you got some sprinkles, some, syrups, some peanut butter cups, Heath bars, whatever you like to put on your ice cream, gummy bears to choose from. You must follow these rules when making your dessert. Okay, so you're gonna take an ice cream and then you're gonna put some toppings on it. Maybe what are the constraints about the combinations that I can do? There must be exactly one ice cream base. Okay, so you can't mix ice creams together, right? You choose a base. You either buy mint chocolate chip or you buy vanilla or you buy chocolate. You can't combine them, all right? You can add one or more types of toppings or have no toppings at all. All right, so I can add sprinkles or I can't add sprinkles. I can look at each topping. And decide if I want to add it or if I don't want to add it. And there are at most two of each type of topping. Okay, so I can add like 2 scoops. Like, when you get ice cream, like, could I get sprinkles? They might put a scoop of sprinkles. So I could do 0 scoops of sprinkles. I could do 1 scoop of sprinkles, or I could do 2 scoops of sprinkles. Okay. Interesting. Or I could do, so I could do that for each topping, right? Like I could look at the first topping, maybe it's sprinkles. I could say I want 0 scoops of sprinkles, 1 scoop of sprinkles, 2 scoops of sprinkles. Then I look at the next topping, maybe it's gummy bears, and I say, okay, I want either 0 scoops of gummy bears, 1 scoop of gummy bears, or 2 scoop of gummy bears. And I can do that for all of the M toppings, and then I'd add that to the one of the N ice creams that I chose. You ever been with somebody who you lose respect for because they just put a ridiculous number of toppings on their ice cream? It's like, come on, man, you got to grow up. You have gummy bears, syrup, Heath bar, peanut butter cup, ketchup, Diet Coke, all on your ice cream. Like, this is ridiculous. Okay, so you're given 3 inputs: base cost, an integer array of length n, where each base cost of I represents the price of the ice cream base flavor. Okay, so you're just given a list of numbers, right? And each of those numbers are the cost of that associated ice cream. Topping cost, it's the same thing, but it's the price of the topping, right? So then you just have a list of numbers, and then each of those numbers represents the cost of using that topping. We don't know what the toppings are. We don't know what the ice cream is, I guess, but that doesn't really matter. Target, an integer representing your target price for the dessert. So I guess you walk into the ice cream store like, I have a target price that I'm trying to hit. I'm trying to spend $15 total on the ice cream that I buy right now. You want to make a dessert with a total cost as close to target as possible. Yeah, so I want to build up. Ideally, I'd spend exactly target amount of money on this ice cream, right? But I'm going to use all of these different ingredients and different base ice creams and see if I can make some combinations such that the price is as close as possible to target. And then you're going to return the closest possible cost of dessert to target. If there are multiple, return the lower one. Okay, so I guess that's saying is like, if the target price was 15, right? Maybe I find a way. I look at all the ways that I can build this ice cream. And if the target price is 15, well, maybe I find a way where I could spend a total of 13, right? And then I find another way where I could spend a total of 17. And those are the 2 closest to my target price of 15. I would choose 13. So I'd always choose the smaller one if they're both the same distance from my target price, right? Because I'm looking for prices that are a distance from the target price. So the absolute difference between the target price and the price that I'm able to calculate. Okay. So when you have 1, 7, right? And the target is 10, well, what I could do is I could choose this base cost of 7, and then I choose one of the toppings of 3, and then get to 10. So how would you approach this problem? Now, I think one thing to notice when you look at this problem is look at how small the constraints are for n and m, right? So since n is less than or equal to 10 and m is less than or equal to 10, This is a really small system. So that kind of indicates to me that this problem can probably be solved, you know, efficiently enough. I don't know if it's the optimal solution, but efficiently enough by just brute forcing your way through. Now, if I wasn't given these constraints, right? If I was in an interview context and someone gave me this problem, it would be problematic. The problem problematic. It would be troubling. It would be difficult if the constraints weren't given, because I might look at this and think of, obviously there's a brute force solution, right? Obviously there's a brute force solution where I could just figure out how to enumerate through every possible ice cream combination with every possible topping combination and return the one that's as close to target as possible. But I'd maybe go down this rabbit hole of thinking, oh, what if there's a better solution? What if there's a dynamic programming approach, right? What if there's a prefix sum approach? What if there's some sort of way I can model this as a graph and solve it that way? And I might end up wasting time when there's a sufficient solution, at least the way that this problem is stated, where you can just brute force your way through. Right? And brute forcing means looking at each possible combination and finding the total price. So that's essentially what we're going to do. So how would you do that? So if you had your base costs, right? So you can only use one of each base, right? So I could say, I'll look at each possible base and I'll build all the topping combinations on top of that base, right? So what I mean is, like, I have base 1, right? Base 2, base 3, and those have associated costs, right? And then from there, like, so if I looked at base I, right? So imagine I used this, I'm going to look at each base, right? But for example, when I'm looking at base I, so it's like maybe it's vanilla. So I'm looking at vanilla ice cream and it has a certain cost. Now, I have to look at each topping and make a decision about if I'm going to use it or not, right? So if I look at the first topping, right, either I use the topping, I don't have to choose the topping, right? So I could do 0 of the first topping, right? I always have that choice. I could also do 1 of the first topping, right? But I can only do at most 2 of each type of topping. Or I could do 2 of the first topping, right? Those are my choices, right? I can choose 0 of the first topping, I could choose 1 of the first topping, or I could choose 2 of the first topping. And then I play the same game from here, from this state, with the remaining toppings. Right, so I could do 0 of the second topping, I could do 1 of the second topping, or I could do 2 of the second topping. I could do 0 of the second topping. I could do 1 of the second topping. Or I could do 2 of the second topping. Right, I could do 0 of the second topping. I could do 1 of the second topping. I could do 2 of the second topping. Or whatever. And then I just keep going down this path, right? And then when I get to the end of the system, if I summed up the cost of this path, right, that'll give me the cost of using that combination of toppings, right? So if we looked at the first problem quickly, so we have base cost equals 1 and we have base cost equals 7. So I choose one of those and then I look at each toppings, right? So I could use 0 of the first topping, which is 3. I could use 1 of the first topping, which is 3, and I could use 2 of the first topping, which is 3. And then I could go into this state and I could erase all this because it's making everything convoluted and look confusing. Or I could do 0 of the second topping, which is 4. I could do 1 of the second topping, which is 4. I could do 2 of the second topping, which is 4. And then the same thing here, 0 times 4, 1 times 4, 2 times 4, 0 times 4, 1 times 4, 2 times 4. Right? Now this is using everything with the cost of 1. Right? So I basically have enumerated, like, okay, what are the total costs of using, what am I saying? These are all the possible prices of using this base, looking at all the possible toppings, right? So if I just summed up this, so what's the length of this path? Well, that would cost me $1, right? This will cost me $1. If I just chose this ice cream and I chose no toppings, if I chose this path, that would cost me $5, right? Because I use this topping with this base, right? And then I'll just quickly go through the rest. right? So if we just figure out what these prices are, so this is 8, 9. If I use from here to here, I cost $1 to get this ice cream. I spent $3 to use 1 serving of this ice cream and $0 to use 0 servings of the second ice cream. So that's, I'm just summing up these paths. That's pretty much all I'm doing, right? So it's 4, 7, 8, 8, 11, 12, 6, 7, actually 6 plus 4 is 10, 11, plus another 4 is 15. Okay, so that's the prices of using all of these ice cream combinations, right? So I pretty much know the cost of everything associated with using, this topping or whatever. Okay, and then what I can do is just kind of, I can copy this system here. Right? And then I can look at the next ice cream that I can use, which is 7, which would then just make all of these 6th grader, right? Because the previous one was 1 and this one's 6th grader. So if I just did the same thing and summed all these paths, right, everything would be 6th grader. So 6, 7 plus 4 is 11, plus 4 is 15. This is 6 is 10, plus 4 is 14, plus 4 is 18. Okay, this is plus 6, 7 plus 6, 13. 13 plus 6, 4. Whoa, what do I do? 6 plus 7 is 13, plus 4 is 17, 21. Okay, sorry. So this is then the cost of using 7 as your source, right? And then, so now we've essentially found, we found all the costs from using this. We found all the costs from using this, right? So now we just look at whatever one is the least, right? So which one's the smallest? This one, right? Which one's the closest to target? This 10 here, right? So all we have to do for this problem is we can literally just enumerate through every single possible combination of topping prices. And then once we get that, return that to the user, right? We just find whatever one is the minimum. So we basically exhaust all possible ice cream topping combinations. We look at the total cost, we compare it to our target, and we return the minimum one. Okay. Yeah, so what's the runtime of doing this? So you might be like, okay, this is crazy. Well, we have to look at each N ice creams, right? And then we have to make a decision about all of the toppings, right? So there's M toppings, and we have to basically branch out 3 times, right? Because we have to we either don't use the topping, right? We do use the topping, or we use 2 of the toppings, right? So there's 3 options for all of these, right? For all M of them. So that's N times 3 to the M, right? Because there's M3s, because there's M cases where I have to choose either 0 or 1 or 2 things. So that gives me 3 options. And then the N's here, right? Because for this example, right? There's a 0 path here, and I either choose this one or I choose this 7, right? So, yep. So that's ideal. That's exactly how this problem works. And then N times 3 to the M, well, we have, N is less than or equal to 10, M is less than or equal to 10. So what is 10 times 3 to the 10? This, right? So this is fine, right? What you're trying to get to is this is This is scalable to almost 1 million. What is that, like 10 to the 6? So, 10 to the 6 operations is doable. It's feasible. It's kind of getting to the edge, right? Like, okay, this is starting to become a lot of operations, but it's not that bad, right? Okay. So I guess one last thing we could think about if we wanted to get rid of a factor of n is that we're doing all these same calculations over and over again. So maybe if we found this tree once. Now, I don't even think we need to do that because an extra factor of 10 isn't going to kill us here. So I'm not going to, I'll make a comment about that when it's done. So what we'll basically do is we'll convert this tree into code by keeping track of the total cost so far and looking at each possible topping, right? So we'll have our best total, self.best total. This will be the total price when we look at each total cost. We'll say, okay, what is the best total cost? And we'll just set it to this so that we can update it with something better. Okay. And then what we'll do is we'll create a function called total cost, all right? And we'll look at TI. So we'll look at a toppings index. Okay. And then we'll look at the cost that we've incurred so far. Now, if topping index is greater than or equal to the length of topping cost, that means that we've already looked at all of the toppings. Or maybe we'll just do less than 0. So we'll go in the opposite direction. No, that makes it seem more confusing. Okay. Then we'll have to make a decision about, okay, the best total cost is what? Well, it's going to be the minimum of using this. So we'll make that decision later. Let's first do this part. Okay, so if I'm looking at a certain topping and I have to make a decision about if I want to use it or not, what does that mean? So I'm going to end up going to the state where I use this topping, so I increase the topping index. So I'm going to look at the next topping next. I look at the current cost that I've incurred so far, and I say, well, either I use 0 of the current topping, right? So I could do that. Or I could use 1 of the next topping, or I could use 2 of the next topping, right? So those are my 3 options, right? So I'm looking at the current topping. Why did I put topping cost here? Right, I'm looking at the current topping at the topping index. And I'm basically saying, okay, either I can use 0 of this topping, all right, and this is going to branch out. Right, so if you look at this problem here, right? If you look at this general case, these are the same things, right? Well, I erased it. That's why, because I'm an idiot. Okay, right, I'm basically, like, this example is this top branch, right? Where I do 0 times the topping. This branch that I'm going to recurse out on is this topping. And this branch is this final topping, right? And then I'm going to add in the cost that I've incurred so far. So when I sum through, I'm just keeping track of the cost that I've done so far so I can get the total cost when I get to the end. Okay. So then how do we make a decision here? Well, how do we know if the total cost of the combination that I found now is better than a previous one that I found? Well, it's going to be the minimum. I look at my cost, the best cost that I found so far, and the cost that I'm looking at now, and I'm trying to find the minimum of what? Well, I looked at the cost, and it's going to be the absolute difference between the target price and the cost that I'm looking at, right? That's how I know. Yeah, because I'm trying to find the closest total cost to my target price, right? So when I get to this point, that means that I've looked at all toppings for a certain base. I've summed up that total cost, and that value is cost. And now I'm going to try to figure out if it's better than a best total cost that I found previously. So in order to do that, I need to look at the difference between the target and the total cost that I found. Okay. So then now what I do is I just say, okay, well, I'll run total cost. So I'll look at each base cost, right? In base costs. And then I'll run TC. I'll find the total cost of starting of using the first topping, so index 0. And the initial cost is just the base cost, right? Because the first thing I have to account for when I'm summing up the price is the cost of the ice cream itself. And at the end, I'll just return the best total cost that I found using this approach. Okay, so for 8 and 10, it's saying 11, but the expected is 9. Why? Well, because the price of the ice cream is 1. I only have one ice cream I can choose from. And if I choose one of this topping, the total is 9. Or if I choose one of this topping, the total is 11. But my ideal price is 10. So 11 is 1 away from 10, and 9 is 1 away from 10. But remember that I'm supposed to choose the minimum, right? So in order to account for this, I'll say, well, if the absolute difference of my total best, if they're the same, I don't want to play this game, right? I'm trying to think about how to do this in a neat way. Let's put this down here. Hey! So I want it to be minimum. So if one of them is smaller, times int no, that's not gonna work. I thought I could get cute with it, but I'm not going to. Okay, so basically if the absolute difference of target minus cost equals the absolute difference of target minus best cost, right? So if they have the same absolute difference, we're going to choose the minimum between them, right? So whoever has a lower cost in total, we're going to choose that. Otherwise, we'll just play the same game. So this is kind of ugly, but it's fine. So we'll run this again. Good. And then we'll just submit. All right, cool. So then what's the run in the space? So this is kind of slow because I think the case is that since we're recomputing all of this, we could compute this system once, right? And for this system, we were already recomputing everything else. So we don't have to recompute it again and again and again. But it's going to use extra space. And since this is so small, right, it's feasible. I'm not going to emphasize that. But you could use some sort of catch to catch information you've already seen, say that information, so it's more of a dynamic programming approach. But since the constraints are so small, I'm not going to worry about it. So this is, we've already just established, right, this is the runtime. Right, and then for space, well, it's going to be the same, right, because you have to create stack space to run this recursive function, and you're going to have to do that for each of the calls that you make. And the calls are proportional to the number of things that you're creating, right? Because the number of times I call this function is really the runtime of, is proportional to the runtime of this function, right? But also, the amount of space we use is defined by how many times we have to call this function to create stack space. So The number of times we create the function is the number of times we run the function. The number of times we create the function is the amount of space we have to create for the function. So those two things are equivalent. So the runtime and the spacetime are both n times 3 to the m. So just to put that here, big O of n times 3 to the m. And space is O times n times 3 to the m. All right. Peace out, guys.